Test. Hello, we have sound. All right. Hello, everyone. Welcome to. This is going to be the first lecture of two parts. So there's part one and part two for Biostats this summer. This is the whole part one and part two are for your knowledge, FYK. So just go through them if you like. Don't worry. Don't stress too much about it if you don't want to. I'll put up the slides. And I'll put up the two PowerPoint presentations. You guys have the integrity if you want. This is going to be just kind of a summary overview and then highlights for specific. So biostats is a giant subject. The research and statistical methods for is a giant subject. So I wanted to make sure it was a little more focused for you guys. And so with these two PowerPoint presentations, it's more stuff that I think will be more relevant when you're out in practice. And it's just really going to depend on where you end up practicing. So for me, out of my practice, it really wasn't until academia that I had to look at this stuff again. So I kind of learned it for the exams and then forgot it. It just kind of depends on where you work. I know there's other pharmacists that use it more. And so I think it's the similar thing for PAs. It depends on what line of work you end up in, what type of clinic setting, etc. But I think a basic understanding and basic foundation is good, just because the drug reps are going to be out with their latest research papers and stuff, and so you at least be able to kind of browse through it, look through it, and kind of judge whether or not it's a good paper or not. Okay, so and apologies ahead of time. It's both presentations are just a lot of definitions. It's a lot of just defining things, a lot of vocabulary, a lot of new stuff. I can't remember if you guys had to take statistics or not before, but stuff you've seen. If you have taken statistics, you'll see some of this stuff. Some of it will be review, but sorry. Hashtag not sorry. No, I really am sorry. This is boring for me too. So let's get to it. Nothing to it but to do it. So first, with statistics, you'll hear them described as being descriptive or inferential. So descriptive, pretty self-explanatory to describe something. So a lot of times you see, like, for example, age of patients, hair color, height, whatever. Those are descriptive statistics versus inferential is something that you have to infer, which is also like saying you're making a prediction of something. So this is where you try to make a prediction about the population. And you guys have probably heard me say this before. I say it all the time. It's one of my favorite lines that my wife rolls her eyes at and doesn't ever laugh. But it's where humans are really good at making predictions about the future. We're just really bad about being correct about those predictions. So when you see inferential statistics, always keep that in mind, that they are here, beware of their potential fallacies, errors, and biases when you're making predictions. So I'll make a prediction about the class based on my biases, etc. So when I'm writing an exam, I'm making predictions or whatever, and I'm usually wrong. So happens a lot. But this is where, the rate of obesity students, or for PA students, I'm sure, at a few schools will be extrapolated to the U.S. So they'll only do a survey, let's say, at 3 of the PA schools in the West Coast of the United States, and then they'll make a prediction and they'll make an inference. They'll infer that that obesity rate that they surveyed, that they sampled, then is applicable to the rest of the United States. And so, being in South Texas, or as a pharmacy student, a lot of times these national predictions, these national statistics, wouldn't match South Texas and the southern part of the U.S., and then let alone the U.S.-Mexico border, so Rio Grande Valley. Shout out, miss you guys up here freezing in Missouri. No, it's not that cold. It's actually kind of heated up. Everyone's freaking out because it's 90, 92. Okay, so like I was saying to you, you don't need to always keep in mind the potential for fallacies, errors, and biases when reading a paper. And that's just with inferential or descriptive. I mean, that's just a general caveat for all papers when you're reading them. Just definitely go into them very, very skeptical. I was going to say cynical, but not cynical. That's skeptical. And you do have to make inferences. It is something that has to be done, just because go back to the PA school. You survey the ones, let's say on the West Coast of the United States, just because that's where you live or you're around there or whatever. And so it's it would be, I'm going to say impossible, but near impossible to then survey every PA student in the whole U.S. And so it's really impractical. It's expensive, etc. So a lot of clinical studies are going to be using inferential statistics. So you're going to see that a lot, but just keep that in mind, that there are some pitfalls there. And like I kind of touched on this before, but you definitely always want to have professional skepticism. The quote is trust but verify. So my dad's an accountant. A lot of my dad's family, they're accountants, and so, and auditors specifically, and so they always say that's their motto, the accounting motto: trust but verify. But you'll hear professional skepticism is kind of the, so it's not being cynical. Cynicism has a negative connotation. So don't say when you get something, oh, I'm a cynic, let me look, if a drug rep gives you a paper or talks about this great, life-saving drug or whatever, just have professional skepticism, kind of, trust but verify. So I have this photo here, and I forgot, I made this presentation last week, and I was looking at this like, what the crap? Why is that photo there? So this, when I Google image searched professional skepticism, this came up, and I thought it was funny. Specifically, I thought this, I wish I could zoom it. Can I zoom? No, I can't zoom on this computer. I thought this kid's face was funny too, and then this, I don't know. I think it's funny that this is professional skepticism. Sorry. I'm laughing right now. I can't control my laughter. Okay. Sorry, guys, for laughing in the microphone. Types of data. So two main types. And so, well, let's see this. Okay. So here's this visual. I'm very visual, so this helps me a lot. Keep it straight. But this is what we're going to start talking about, these types of data. And then we have, so I'm jumping back. Quantitative and qualitatives. Quantitative, qualitative. So something to do with numbers, right? Quantity versus quality over here. Sorry, I'm still laughing about this stupid photo. This is, I'm sorry, very unprofessional of me. Okay, let me pause it real quick. Okay, I'm sorry. This is so boring. When I was making this, I had to I was doing stupid stuff when I was writing. We just moved. We barely finished unpacking. I was writing this stupid thing. So anyways, I'm sorry. But so qualitative are things that, like I said, it's a quality. It does not have a numeric value, so no numbers. It's very rare in clinical studies. So for the medical, so I'm focusing this for medical professionals, right? You guys. And so this is very rare because it's very subjective. So because if it doesn't have a numerical value, and something, you may see it like with maybe like patient satisfaction or something. I don't know, but it's very subjective. So very unlikely that you'll see that. The main thing that you're gonna have to be worried about with data in the healthcare professions is quantitative. So numbers, they are more objective, and so they hopefully kind of help point you in the right direction as far as what you're studying, what you're looking at. So of the quantitative, then we're going to go down again and go to discrete versus continuous is the next step. And then under continuous is interval and ratio. So interval data has a meaningful numeric value, and their difference between two consecutive values is consistent along a scale. However, there's no real 0 point. So this is like the Celsius temperature scale, or Fahrenheit. I don't know why metrically. But so anyway, so higher temperatures are always hotter, but 0 degrees doesn't really mean anything because they're negative. So you can have a negative 20 degrees Celsius. So anyway, so that's where that's the kind of textbook example of interval data. Ratio data is the same thing, except it does have a meaningful 0 point. So you guys remember Kelvin, not Kevin, the student, no, Kelvin temperature scale. It does have an absolute 0. So, and then other examples you'll see is weight and length. And with continuous data, you can include decimal points. So let's just read through that. Okay, I repeated myself. Sorry about that. So one final point. Okay, so that was a typo. Just repeated myself there. Yeah, so I need to delete that. Let me do that right now before I forget. Ta-da, magic, movie magic. That's a good, I guess that's the advantage of not being live. I'm recording this with the original copy of the PowerPoint, so that I guess that'll be nice this next semester when I'm doing Farm 1 with the newbies. Okay, so then I'm supposed to do one final point. See that makes is continuous data can include decimal points and other non-integers. So if you see 16.57, then it's continuous. Continuous. Oh, I'm sorry. And then we have discrete over here. Discrete data. Data? I go back and forth, sorry. Some students get tripped up because the discrete is under the quantitative. Don't let that trip you up. And some of this stuff, it's like I said, I memorized it for the class, and then I haven't thought about this, since then. But so this helps you describe data that are mutually exclusive, that are discrete from each other. So you cannot be, the textbook example is you can't be two ages at once. So you can't be 28 and 35 years old. One age precludes you from another. So your age is your age. So why is it quantitative? Students sometimes ask, they get confused about. And I'll let you guys read through this. We use it to count up or tally information about participants in the study. And you can read through this example. So under discrete, we have 3 different types. You can see that here, binary. I guess I put this too many times in the slides, but it was helping me when I was getting confused and flipping back and forth. I was like, let me just put this chart again, but all right, whatever. So nominal data, it's definitely things that do not have a numeric value. So this will be something like ethnicity or marital status, and they have no inherent quantitative meaning. So for example, marital status, that doesn't have necessarily a number, or there's no quantitative meaning. And I think that's why sometimes people will hear marital status and they'll be like, okay, this is qualitative, it's not quantitative. But just remember that it is quantitative and it's nominal. It's because it's discrete data. Binary data. So this is with only 2 options. So the classic example is gender, so male or female. But nowadays, with the gender lines being blurred, so to speak, and then historically in some cultures they'll have the third gender, like some Native American and the Hindus have historic tradition of kind of different genders, etc. So you'll see that a lot in the textbooks, but just know that. But anyway, so if you want to remember that as gender, binary data, you can. I still think of it as binary because it's kind of easier to remember, but whatever you want. And it's often lumped together with the nominal data. Ordinal data. So this has a ranking system to it, and the ranking order is important. So the specific, whatever the rank is defined as, you need to stick to it. You can't change it, etc. So example for healthcare professionals with heart failure. So class 3 heart failure is worse than class 1 heart failure. However, the difference between the rank classes is not equal. So class 3 is not 3 times worse necessarily than class 1. Does that make sense? And so anyway, so that's something to take into consideration and kind of think about. And then you'll also see some other examples here that you can read through. They may see in healthcare. So here's some things that commonly trip students up, or trip people, students and professionals, is that discrete data can only be whole numbers, and then if there's any sort of decimal, then it's continuous. And so age, for example, is a common discrete data point, because you typically don't say someone's 34.65 years old. Typically in studies you'll just see them round, and so they'll either say 34 or 35, or they may not round. Maybe say just you're 34 until you're 35, or if you're, I don't know, depends on what the study is, they may put you in the 35 category. Or we'll see a lot of times where they'll have an age range, so they'll put 18 to 35 year olds. Let's say you'll see that. Another point is you're not supposed to convert one type of data into another. So you shouldn't take the nominal date of age and convert it to ordinal by assigning categories. But you can break the ages population into 4 categories. Here you go. But classifying it this way puts it in an order where rank is important, and then it becomes ordinal. Because remember, with ordinal, the rank is important, like with the heart failure classes. Slide transition, another just Google image search, because I was getting, after all that stupid stuff, all those stupid definitions, I was like, I need something else here. But I don't know if you guys remember when computers used to look like this. Slide transition. Definition of a biostat. This is another, I forgot I put this in here. Definition of a woman is it's an R&B song I enjoy. But yeah, you can click on there, and I think it should hyperlink you, hopefully. Definition of a woman. I think I like listening to R&B songs sometimes, and I think they're kind of funny, but really enjoyable, and then I'll be singing along, and Dr. P will be laughing at me. But definition of a biostat. I don't know, again, why I put that there. Sorry, it's been a long couple weeks since I haven't seen you guys in person. It's been like a month, but so anyways. So now we're jumping into some other just definitions here, and again, just apologies all around. I'm trying to make it fun by just laughing by myself in a room with a microphone. All right, so anyways, I wonder if it works if I clicked on it. Live demonstration here, y'all. Oh yes, it works. I know how to hyperlink now. So let's see if it's worth listening to. And by the way, just fast forward through this if you don't. Yeah, it's worth it. It's not picking up on the mic because I have the mic plugged in. Yes, David Hollister. Okay, sorry about that. Okay, dependent variable. This is the outcome of interest, and it's dependent because it depends on the intervention. So this is, classic, I love drugs, right? Atorvastatin compared to placebo. So you'll see that a lot in drug studies. They'll do a active medication versus placebo. And to see if it has an impact, let's see, for example, on secondary cardiovascular events. And so the dependent variable is the number of cardiovascular events. And so we're testing the likelihood that this secondary coronary vascular disease, if a patient, and whether it depends, I'm sorry, let me start over. I got tripped up there. It's like, it'd be cool if I had a producer be like, all right, you just let's cut it, rewind it. All right, we gotta go back. I don't edit here. I'm sorry. So we're testing the likelihood that the secondary cardiovascular event depends on whether or not patients take atorvastatin. So is the drug efficacious, or does it work to help reduce coronary vascular disease? Independent variables are the intervention, the thing we are manipulating. And so the independent variable in the previous example would be the drug, the medication, atorvastatin, and it does not depend on any other event. Population. So this is just the population you're interested in, the people, the group, etc. So going back to that atorvastatin example, all the patients with a prior coronary vascular disease would be the population. And so this is the entire population. And so they typically, again, just not feasible to study the entire population. And so they will use a sample, which is represented by the letter N for Ned, I guess, N for Nancy. But yeah, so sample, they'll use a sample because you can't test the whole, population of a country or a city or town, whatever. And so sample is also known as a study population. Like I said, it's abbreviated N. So that's why I'll say sometimes it's like N equals 1 is anecdotal evidence. I don't know if I think I've said that to you guys before. I say that a lot. N equals 1. And again, my wife rolls her eyes. But so when something's anecdotal, or rather it's just maybe a once in a lifetime kind of event or whatever, they say that N equals 1. So the sample size equals 1, and it means it probably shouldn't be extrapolated and kind of generalized to the entire population. But and the other thing too is you typically, the bigger the sample size you can get, the better. And so I mentioned the entire population is too large, right? And so that's an impossible thing to do. But you should, the kind of best practices, the idea is that you should get the biggest sample size you can, and then the most representative of the population that you're going to be talking about. So if you are interested in talking about if a medication works with Hispanics or not, you'd want to get the biggest group of Hispanics you could, and not have a mix of non-Hispanics in there, because then it wouldn't be, appropriate then to talk about, this is happening in Hispanics. And you can get even more specific too. You can get Hispanic men, Hispanic children, Hispanic women, etc. But definitely this is important to look for when you're analyzing a study. So because Caucasian males are usually overrepresented in clinical trials. So again, that was happening again during rounds and during our rotations and stuff in pharmacy school. They would be like, okay, well, this study is from, like, I don't know, I guess sound racist, but what's some, like, well, Missouri, there's a ton of white people up here, a ton of Caucasian males up here. That was one kind of culture shock when I came up here. But so let's say they just sampled Missouri, central Missouri. There's not a lot of Hispanics up here. There is a Mexican grocery store down the street, which I was surprised that I was like, okay, cool. It's a little one. It doesn't really have much, but anyways. So if they did a study based here, and then I was a pharmacy student in South Texas, that is something to take in consideration. It doesn't mean that you completely ignore the study and you're like, well, whatever, it was for white people in Missouri. No, you still look at it, but it's just, again, something to think about. So the sample size and then the sample demographics, are very important, and definitely look at those. And then, make sure it's an accurate representation for what conclusions they're making. So again, to use that in Missouri example, they do a study here with predominantly white males, and then they make a generalization, or rather than they claim that atorvastatin is going to work this exact same way as it will in South Texas with Hispanic males. And so that would be something, or a potential red flag that you'd have to look at. And so always, students, and I know myself included, before Biostats, I never really thought much of the sample, but there's a big, it can have a really big impact on the results and then the reporting the results, etc. So check out your sample. Sample your sample. Okay, again, just basic definitions. It's probably review for most of you guys. But mean is just the average of a sample distribution. And this is how you math alert. Mean equals sum of all values plus number of values. So I think you guys know how to get an average by this point, but it's not bad math. You just add everything up and then divide by the number that you have, the number of values that you were given. So the weakness is that it is very sensitive to outliers. So those extreme sort of plus or minuses depending on the data. So you look at, for example, if you have 4, 12, 8, and 100, then the mean is 31. So because of this, one of the values is 100, it's going to really shoot the mean up. So because the majority of the numbers are, you could say, we could factually say are below 15, right? Or they're below 13. I don't know why I picked 15, but let's just say they're below 15 just because it sounds nicer. I don't know. And then, but then the average is almost double 15 because of this number 100. So it's an outlier. And it can only be used for continuous data. So that's just kind of a note. Just make sure you look at that, and you guys can read through this. So the median is like on the highway when you're driving, the median in the middle of the highway. So the median is the middle of the list. So you have to first get the numbers rank and put them in numerical order, lowest to highest, and then it's the number in the dead middle. If you have an even number of values, then you need to take the average of the middle two. So I gave this example here. So same for numbers, and we lined them up lowest to highest, and then we take the average of the middle, and that's 10. So this actually helps with that, or helps you see better where the data or the numbers are kind of clustered or where they fall. So again, majority of numbers are under 15. The median is 10. That's actually shows you that more of the numbers are going to be, are smaller. And the number 100 here has less of an impact on the median. It actually has, I guess, no impact on the median other than it's not in the middle. But anyways, oops. Whoa. Okay, so the mean was 31, median is 10. And like I mentioned before, the strength of it is because of those outliers. It doesn't, it's not as susceptible to being skewed with outliers. Well, it's not susceptible at all because it just takes the middle number. And it can be used with both continuous and ordinal data. Mode, I put this, oh yeah, because in French, mode means fashion, I think. Let me double check. Yes, it does, because I put it on the freaking slide. Okay, sorry. I promise I'm not losing my mind yet. Okay. And so that has nothing to do with biostats. But again, like I said, when I was making this, I was getting bored easily. So this is the number that occurs most frequently in a data set, the mode. And I just memorized that. I don't know. I can't think of when I remember in school when I was first taught this, it was like, what? That's so random. I got mean. I don't know why I just felt like that was average. Maybe someone told me that before. Median because of the highway thing, I always remember. But then mode, I was like, mode, I don't, but it just, other than meaning fashion in French, it is the most frequent. Oh, maybe you get like trendy fashion, mode, and it's like the clothes you see all the time. Maybe that, but anyways. So, okay, occurs most frequently in the data set. So this previous example we used doesn't have a mode, by the way. Range, that's the difference between the highest and lowest values. And so this lets you know about the limits of expectations of effect. So for example, with an intervention, I like this example here. So you measure the LDL for 1,000 people, and then you give them a statin for 3 months. And then after the 3 months, remeasure their LDL. If the highest reduction was 40 and the lowest reduction was 5, then the range is 35. So 40 minus 5 equals 35. And that gives you an idea of when you're prescribing a medication, it'll give you an idea, okay, this is torvastatin. When we're going to measure your LDL and we're going to recheck it, it will hopefully go down, between 40 and 5%, at least, 30 so or whatever. So anyway, so that's a good thing for you guys. It's also a measure. It also measures how precise or consistent a data set is. So the larger the range means that the effects of intervention can vary greatly between individuals. So to use this torvastatin example again, if the highest was 40 and the lowest was 30, then that would be a much smaller range. And so you could have, you can predict a little bit better what type of effect the intervention should have. So with your patient, if we're expecting between a 30 and a 40%, that's a pretty precise range. You don't really see that a lot, unfortunately, but anyways, and then the larger range, because with the larger range, it'll be harder for you to quote unquote predict for your patients if they're going to have how much their LDL is going to go down. Okay, so normal distribution, you have also probably heard of it being called the bell curve because of its shape. So this is where you hear anybody, or where you hear people talk about like breaking the curve or a curve buster, or I'll look at it. We look at the curve for grades, and this is actually where you get the slang, I guess, for curving the grades is when the grades don't fit the bell curve, then you have to curve them so that they kind of fit the bell curve. So I say curve a lot, but normal distribution to me is kind of a better label in the sense that it's more descriptive than just saying a bell curve. So this mathematician, Gauss, I guess Carl Friedrich Gauss, but anyways, he's a German mathematician. He focused on the probabilities of distribution, and he developed the central limit theorem. And click on those if you want to. Don't worry about it. If you don't have to go and read. It's just, I think, Wikipedia. So the central limit theorem, the averages of random variables draw from independent distributions, coverage to normal, I'm sorry, converge or convert to normal, assuming the data set size is large enough. So you look at the heights of enough humans, then there should be a normal distribution, quote unquote, or a bell curve of the height. And again, if you have a large enough data size. So if you only look at, 5 people, you probably won't, especially if they're related, you probably won't get a bell curve or have that kind of nice curve distribution. But if you take the whole population of McAllen, Texas, let's say, then you should have more of a bell curve distribution of height. And so your population will have a Gaussian or normal distribution. I feel like people used to say Gaussian more, Gaussian distribution. You still may hear that, you may read that, it is still in textbooks, etc. And so Gaussian is giving a shout out to Gauss, the guy who did. But most people, and I like to say normal distribution, just because it's easier for me to remember. And then I'm always like, I don't know how to say that. What, am I pronouncing it right? I don't know. I had a couple of German friends in college, actually an undergrad and graduate, and there was a girl from Germany in pharmacy school, and they were always on me about my pronunciation of German. I'm like, I don't, and then they're like, oh, it's horrible. It's, I was like, I won't do their, I won't do a German accent here and make fun of them, but they were like, you can't, like, you can't speak German. And they were saying how like non-German accents are horrible and stuff. I don't know. But anyway, so now I'm all embarrassed anytime I see a German word. I'm like, I don't know how to say that. But anyway, so yeah, bell curve. And it turns out that most populations for just about anything will fit a normal distribution. Again, caveat, if the sample size is big enough. And so this is what it is. This is, it is what it is. No, this is the bell curve, the normal distribution. And we'll talk about all these other things here in a little bit. But so this is where we'll say grades, and it'll say, so this is 70, this is 100, this is a 0. This is kind of what you'd want the grades on exam to look like, close about. I usually try to do that. Mine's 80. I try to have this as 80 since the department has that as its kind of cutoff. So this is where I want the majority of students to be here, because again, this normal distribution. I mean, I'd love for everybody to make 100, right? I mean, don't get me wrong. And I think for this class, my curve will be shifted. My hump will be like, woo, over here, I think. For this class is my prediction. So typically in clinical research, when a study population is large enough, it can usually approximate the normal distribution. And the mean, median, and mode are all the same value, right? Mind-blowing. But yeah, so mean, median, and mode, which is kind of nice. They all are there because what's in the middle, the median, it's in the middle. What's the average? I mean, you can do the math, but just trust me. Here's the average. Add them all up and then divide by how many you have. You get the average. And what is what am I forgetting? Mode. The mode, the most repeating number, again, is up here too. So that's kind of cool. And that is at the 50th percentile. And it's also symmetrical around so you'll notice that there's no skew, as they say. There's not a hump over here. There's not a hump over here. The tails aren't, and these are called tails, by the way. Tails and humps is what they're called. And I always think that my milkshake brings all the boys to the, I don't know why when I say humps. But anyways, I'm going to stop saying that. And there's no skew. If the population isn't large enough, you probably will have a skew, and you probably won't have you probably will have a shape that doesn't look like this. So like I said, you just sample a handful of people with their height or whatever, and then you'll probably, I don't know, if they're a tall group of people, the hump will be over here. If they're really short, if they're a shorter group of people, the hump will be, I don't know. It just won't look this nice. So standard deviation, also known as variation, also known as dispersion, also known as measure of spread, not also known, so it's not a spread head. I put that in there. And you know what? I don't have my blackout. Let me, so it's not a spread head. So definitely black that out on your side. I just thought that was funny. And so I put that there. But it's not funny. All right, magic, it's gone. So it's variation, dispersion, measure of spread. I like standard deviation the best. That's the one I use, and that's, I feel like most people refer to it as that, but you may see it with these other handles, but standard deviation, and then sometimes abbreviated SD. But then the standard deviation will tell you how spread out your data is. So if you have a low standard, let's go back here, and this is talks about these are standard deviations here. They're shown on this graph here. 1 standard deviation, 2 standard deviation, 3 standard deviations. So if you have a low or small standard deviation, then your data is tightly clustered around the mean. So you have a very steep, skinny bell. And then vice versa. If you have a very high standard deviation, your data is more spread out. So you have a much more flattened bell, and it's a lot wider. So to use the LDL example again, if you're measuring the ability of atorvastatin to lower LDL by 20% and the standard deviation is small, that means that, yay, hippie hooray, that the majority of patients achieve their goal, 20%. If the standard deviation is very large, sorry, I'm putting myself to sleep, I'm yawning as I'm reading this example. If the standard deviation is larger, then a smaller number of patients will have the effect. I should get like a sound effects guy in here with me and just like does, and it'd probably be annoying. You just sit there for like an hour just looking at me talk to a screen. Then a smaller number of patients will have the effect. So that's how you use it in clinical. That's how you use it in clinical medicine. Here we go. Here's the standard deviation again. Just so you can see that. So the mean is also denoted as mu, which is here abbreviated here, mu. And then mu plus 1 or mu minus 1 is 1 standard deviation. So we have that. Plus 1 minus 1, 1 standard deviation with 68% of the data. And standard deviation is also denoted with the lowercase sigma. So we have this. So mu plus sigma is 1 standard deviation, mu plus 2 sigma, 2, mu plus 3 sigma, 3. And then you can go in the negative direction as well. Okay, sorry, I can't stop yawning. I quit caffeine, by the way. I forgot to tell everybody that. But yeah, I weaned myself. I got on green tea. I'm like a junkie. And I've had a couple relapses, but anyways, and I just don't sleep at night when I even had I had a hot chocolate the other day at Starbucks, and I was like a meth addict the rest of the day. I don't know what they put in their hot chocolate, but my wife and I were laughing about it. We split a freaking hot chocolate. We both have caffeine now. We split a half chocolate, half hot chocolate, and we were like meth addicts. We were like, vacuuming at 3 a.m. or whatever. No, our daughter was sleeping. That's an exaggeration. But, just doing hyper. We were just all hyper and spazzed out. It was before she started working. We were walking around Target. We're like, yeah, you just kick it in for you. Yeah, it's kicking it. Or is this kicking it? Yeah, we're kicking it. We're like high-fiving each other. But yeah, it was like really, I don't know. Maybe I still need to look this up. Maybe they put espresso in hot chocolate at Starbucks. Curse you, Starbucks. But anyways. So yeah, I'm off caffeine now. But that's probably why I'm yawning, because it's boring presentation. Okay, so, and I mentioned before, you can tell how much of the population you're dealing with depending on the number of standard deviations you go out. So that's a big reason why I like this, because it's kind of an all-in-one chart for standard deviation. So if you're told that it's within 3 standard deviations, it's almost the majority of the population. It's 99.7 of whoever you're talking about. And 2 standard deviations is pretty big too, 95%. And then if someone says, oh, it's just within 1 standard deviation, so you can know that that's it's the majority, but it's about 70%. You can think, if that's easier for you to remember, but technically it's 68%. So yeah, that's what all that says. And the standard deviations help, again, with drug studies, because they help predict the likelihood of how many patients will experience this treatment effect. So with a smaller deviation, it means more patients will achieve the effect. and the opposite is true. And so you can kind of see, going back here, you're looking at atorvastatin or whatever, and if these were smaller deviations, that means that more and more of the patients will have this whatever result, desired result. Okay, and then fun fact, standard deviation can be used for continuous data in a normal distribution. So there can be skewness or skews. So not all data is normally distributed, and it can be positive or negative. And when they're talking about positive or negative, this in the skew direction, it is, so it can be positive, to the right, or negative. But then the skew they specifically talk about is the data and not the hump. So they'll say, so keep that in mind, because that always messes me up, and I always think the opposite is true, but it's the skew is in the direction of the tail. So if there's a big hump on the right, then it would be a negative skew. Am I saying that right? Yeah. No. I'm sorry. That's not the same thing. But so if there's a big hump in the right, then the data is skewed then to the right. There's a positive skew there. So here's a left skew, or negative skewness, where you go to the right, and then the right skew here, because the tail is on the right hand side. So, and I feel like it's really counterintuitive, and even when I'm reading and looking at it, I always flip it in my mind. So please help me, please Lord help me. No, but yeah, so please make sure you keep that straight. So if a left skewed, it's talking about that the tail's over here at the left, but then everything is actually shifted over to the right. There's also negative skewedness versus, and I think I just said it wrong. I think I just said it wrong on this other one. What was it? Yeah. I think I said it wrong here, so sorry about that. So this is definitely right. Left skewed because the tail's over here and everything's over here to the right, and then right skewed has the hump over here to the left, and this is considered positive skewedness. Which again, I just have to look at this every time because it's, and good news is usually if there is a skewedness, they will give a visual representation, which helps me tremendously. So, but if that happens, you'll notice the mean then shifts down here, the median is here, and then the mode is up here at the top of the wave, and the same thing here. That it shifts the median and mean. Oops. And they are not all equal. Like I said, the mean, median, mode are not equal. And so make sure you keep that straight too. Now we're going to be changing gears here, and again, going to things that confuse me because it seems like backwards and kind of inconsistent kind of definitions and stuff. But anyway, just stay with me. So the null hypothesis you'll hear a lot about. And that is stating that there is no difference between the treatment groups in the study. So there's no difference if you give atorvastatin or if you give placebo, is what the null hypothesis is saying. Or paroxetine is another example. So if paroxetine versus placebo to treat major depressive disorder, so then the null hypothesis would be that paroxetine would be no better than placebo, or placebo, that basically there's no difference. And this is the typical general default setting, and you're supposed to assume that the null hypothesis is true, and that the data, or rather the study, what you're looking at is supposed to prove otherwise. So you're supposed to prove that the null hypothesis is false. So this is an innocent until proven guilty kind of approach, and this helps with helping remove bias. And so because the human brain wants and expects the null hypothesis to be false. So going into a study, paroxetine versus placebo, you're like, of course paroxetine's better than the sugar pill. Of course it's better than placebo. So the null hypothesis helps us from being biased, and then hopefully not saying a drug is better when it's not really better. So it's a natural bias that and it's that bias that we have is a type 1 error, which we'll define later. So we want to assume that the null hypothesis is false. So hopefully to clarify, if the null hypothesis is true, then there's no difference between the two study groups. In this case, we would fail to reject our null hypothesis, which I feel like it's kind of outdated English, or it's like sounds like lawyers speak, or like when you read a contract, you're like, what? Why are you saying? So we're going to fail to reject our null hypothesis. But it's saying that if you're failing to reject it, it's saying that the null hypothesis is true. So, and I don't like this language, but you will see this language used, and I think it's just out of tradition. I don't know. I don't know why they can't just say the null hypothesis is true. It's saying we're failing to reject our null hypothesis. I don't know. And then to make things even more fun, right? I'm using fun. I'm doing air quotes. No one's in front of me, but air quotes. If the null hypothesis is false, then there is a difference. So paroxetine is better than placebo. So in this case, we would fail to accept our null hypothesis. So fail to reject or fail to accept. Those are going to be the two things. But one's basically saying, this first one's saying that the null hypothesis is true, and this one is saying that the null hypothesis is not true. So we are not accepting it. So hopefully that helps. This is how I always feel like my mind's being blown. Shout out Tim and Eric. That I feel like my mind's being blown here. And I think, oh no, I didn't do a video for that. And it just hurts my head. And I always have to look at it. But anyway, so hopefully this helps. Hopefully this slide here will help you, and not, so you don't feel like this. All right, it keeps going. More lawyer talk, more antiquated English. Alternative hypothesis. So this is the opposite of the null hypothesis. And again, it's going to start getting where, or at least for me, I have to keep revisiting it and being like, okay, what's it? So the alternative hypothesis states that there is a difference or a relationship between the two study groups. So this is saying that paroxetine is better than placebo for treating your depression. Would be accepting the alternative hypothesis. So this is when you would accept the alternative hypothesis. If the null hypothesis is true, then there is no difference between the two study groups. So placebo and medication, no difference. In this case, we would fail to reject our null hypothesis, which we've already been over, and we reject our alternative hypothesis. So again, just another layer to that. So, and you'll see this, hear it, read it in papers, etc. But so fail to reject the null hypothesis is the same thing as rejecting the alternative hypothesis, right? Because they're opposites. And then if the null hypothesis is false, and you would fail to accept our null hypothesis, then you would accept our alternative hypothesis. So again, boom, boom, boom. I think this one's linked up. Yeah, you guys can watch the Tim and Eric mind-blowing video here, but that's how I always feel after all this. I'm like, why couldn't they just make it more straightforward? I don't know, but this is the conventions. This is the world we live in. Like my dad used to say, buddy, life's not fair, buddy. Buddy? He would say buddy a lot when he was trying to teach me about how life's not fair and how it's complicated. So this is one of those things where it's annoying, but this is just the way it is. And this is how you feel afterwards. All right, changing gears a little bit. Again, like this whole freaking presentation. P-value. You hear a lot about the P-value. So the P-value is a measure of statistical significance. So you're looking at a data point in a study, you'll see these P-values in parentheses. There'll be P, and they'll have, less than, equal to, less than, greater than, equal to after it. Then the authors are stating that the finding was statistically significant. And so again, by convention, I'm not going to get into the details, and honestly, I don't really fully know the history behind it or whatever, but for whatever reason, a line was drawn in the sand, and they said, statisticians said, if it's less than 0.05, then it is statistically significant, but if it's greater than or equal to, it is not statistically significant. So it is a yes or no scenario. So the result is either statistically significant or it's not. So it's like an on or off kind of light switch. And then a p-value of 0.051 is no more significant than a p-value of 0.08. Both are significant, and that's it. Wait, I think there's a typo there. Wait one sec. Okay, fix that. Sorry. Change that to 0.04. Well, I'm going to post these slides here, so you'll have that. Never mind. Both are not significant, and that's all there is to it. The p-value doesn't say anything about the size of the study. Geez, why does it keep doing that? Sorry. Also, the p-value does not say anything about the size of a study result. And also tells you nothing about clinical relevance. It's just a simple yes or no, statistically significant. Okay, so remember that here. Highlight here. The highlight thing doesn't work on this computer. So anyways, I like highlighting normally, but highlight there. It does not tell you anything about clinical relevance. So a lot of students ask, where does this number come from? Does it have to be that? It helps to think of it a percentage. I think that'll help kind of clarify it. The p-value is the probability that a study result was obtained by chance. It is yet another safety net to help us preventing a type 1 error, rejecting a null hypothesis when it's true. When it is true. If p is less than 0.05, then there is less than a 5% chance that the result was obtained by chance. So you can say, I'm more than 95% sure that this result is accurate. So it's basically saying that there's less than a 5% chance that it was just that was a fluke thing and that it happened for a reason. So if paroxetine is shown to be better than placebo with a p-value of less than 0.05, then it wasn't a fluke thing. It's more accurate, it's more true, it's statistically significant. So where does 5% come from? It's arbitrary. So there's a consensus that 5% chance of error is acceptable for most studies, but you will come across some that have a lower p-value. So you'll see a p-value of 0.01, which means that the study has only a 1% likelihood of occurring by chance. So that would be better, so to speak. But again, 5% is the cutoff. So 0.05 is what you want to look at, that or below, and then it is statistically significant. There are problems with p-value. So this is not safe for work, NSFW. Last week tonight with John Oliver did a nice summation of that, of some of the problems with p-value, with the p-value, because there is such a thing as p-hacking, or also known as data dredging, which you can read about there in Wikipedia, also known as data phishing, also known as data snooping, also known as data snoop doggy snooping. No, that's wrong. I'm gonna edit that. Okay, the rest of those are true. But yeah, so they have all these different. You'll hear p-hack. I have heard p-hacking, p-value, data phishing, data dredging. But it's basically, and I think this video does a good job, and it's funny. I think it's funny. It does a good job of explaining it. But it's basically where you statistically manipulate the data, the numbers, to lower your p-value. So it's purely mathematical, and then that's where you'll get some kind of crazy results and stuff, or rather, you'll hear some crazy studies about certain things that are, whatever, doing better. But anyway, so yeah, I don't want to give too much of this away, but yeah, this is a good video if you guys have time for it. I know you guys are super busy this summer, but oh, there we go. All right, so changing gears again, we have confidence interval. So this is an estimate of the range in which the true effect of the treatment lies. So this is basically, how it helps give range and context to the sample statistic. And it's used to account for an inherent error of using the statistics of a sample population to derive conclusions about the entire treatment of the population. So because it's impossible to measure the entire population, you instead use a sample population as a proxy to approximate the treatment effect for the population as a whole. So, for example, if we have a patient taking a new medication, lose 10 kgs, with a 95% confidence interval of 6 kgs to 16 kgs. The authors are saying we are 95% confident that anyone who takes this drug for 90 days will lose between 6 and 16 kgs. The confidence interval is trying to add a range to the sample statistic, and the purpose of this range is to apply the sample statistic to the true population parameter. So if there's a 95% confidence interval, then there's a 5% degree of uncertainty. 95% is the conventional accepted confidence interval, so it's like the p-value being 0.05. 95 is where they've, but you will sometimes see that the 99% confidence interval, so it's higher, and there's only 1 degree of uncertainty. And then you sometimes see them lower too, so they'll only have a 90% confidence interval. You should never see a 100% confidence interval, so if you ever see that, it's a big red flag in a study that's impossible and impractical, because that would mean that no one's 100% confident about anything. No, but it just means that they are lying, I guess. I don't know why they would put that, but they'd have to measure the entire treatment population. The confidence interval can also help with determining statistical significance. So if the confidence interval for the difference in efficacy between two groups in a study contains 0, then you cannot exclude the possibility that there is no difference between the two treatment groups. So for example, to help with that, so let's say that the confidence interval is different. So the study participants lost between -2 kgs and 15 kgs during the treatment. So losing 2 kgs is the same as gaining 2 kgs. And then at some patients, if it crosses 0, that means that some patients lost nothing. So therefore, you cannot say with certainty that the results are statistically significant, because the weight loss included 0 kgs, which is no weight loss. So it's not statistically significant. So definitely note that if you see a confidence interval that includes 0, then the results are not statistically significant. If you're dealing with relative risk or an odds ratio, which we'll define more later, and the confidence interval includes 1, then the result is insignificant. So specifically just for odds ratio and relative risk, if it includes 1, it's insignificant. Everything else includes 0, insignificant. Type 1 error. We've been talking about this a little bit before, but this happens when the null hypothesis is true, but the researchers rejected an error. So it's saying that there is no difference between placebo and paroxetine, but you are rejecting it. You're saying that there is a difference, when in reality there is not a difference. So it's a type 1 error. So it's saying this drug has an effect, Yahuza, when it actually does not. That's Yahuza's from one of my daughter's shows. I can't believe I'm saying that out loud. The little characters say Yahuza. Sorry. So it's rejecting the null hypothesis when the null hypothesis should not be rejected. Come on, you're going to hurt its feelings. It's actually true. Come on, don't do that. Type 1 error is related to p-value. If your p-value is less than 0.05, then you are saying that there is a less than 5% chance that we will falsely reject a true null hypothesis, i.e. fail to accept. And then if its p-value is less than that, then there's a 0.01, then there's less than 1% chance. So the p-value, in other words, or another way to think about it, is the likelihood that you've committed a type 1 error or incorrectly rejected a true null hypothesis. That's why you like to see a low p-value, because you don't, if you had a really high p-value, then you could be committing a type 1 error. And nobody likes anybody that commits a type 1. No, I'm joking. And then that would mean that there isn't really a difference between placebo and the drug, for example. So that would be bad. And then, because then you just expose people to side effects, etc., and it's not really helping them. So also on diagnostic tests, you may also see a type 1 error. and that is also known as a false positive. So, which we're going to talk about diagnostic tests a little bit more later. Type 2 error. In the opposite situation, type 2 error is when the null hypothesis is false, but is accepted in error. So this is saying that you claim that there is no difference between the drug and the placebo, but in fact there is a difference. And so this is a type 2 error when there actually is a difference between the two treatment groups, but the researchers say there is none. So you're accepting the null hypothesis when it's actually false. Type 2 errors can actually happen frequently in clinical trials if enough patients are not enrolled. So that's why your N needs to be a big number of samples. Well, this is one of the reasons why it's good to have a large sample size. So N equals something big, a big number. This will help mitigate type 2 errors. And then on diagnostic tests, type 2 errors will be false negatives. So type 1, false positive, type 2, false negative. Now we're switching gears a little bit. Statistical power. So we talked about p-value being related to type 1. Well, statistical power is related to type 2 error. So we use the p-value to determine the likelihood of type 1, and then you look at the statistical power to determine the likelihood of a type 2 error. Not type 2 diabetes, type 2 error. I almost said type 2 diabetes. The actual definition of statistical power is the probability of rejecting the null hypothesis when the null hypothesis is false. So power, I got the power, determines, sorry, I like bad song Tourette's. Sorry about that. Power, I've got the power, determines, I even had to say it, I couldn't even just not. It determines the ability of a study to detect a significant difference between treatment groups. Much unlike the Power Rangers. So shout out to, I think it was Hayden was dressed up as a Power Ranger for Halloween. Statistical power. So as I mentioned before, the conventional default accepted p-value is 0.05. So 5% of committing a type 1 error. The conventional default setting for statistical power is 80%. So if a study is powered at 80%, this means that there's a 20% chance of committing a type 2 error. And the mathematical formula for power is 1 minus beta, where beta is the false negative rate. That's just FYI, don't worry about that. So just like with the p-values, you can make a study more powerful. But again, 80 is the cutoff. That's the one you have to remember. Power 80, p-value 0.05. And you will come across a study with the power set at 90%. That can happen. You can see people, they're just more powerful. No, there's more powerful studies. Only 10% chance of committing a type 2 error. So power is determined by a lot of different things. I'm not a statistician. I forgot I put that. Made me laugh now. But yeah, I'm not a statistician. So it's just, and don't worry about it. There's a lot of things that go into it. But you do need to remember that the easiest way to increase statistical power is to increase the sample size. So another reason why sample size is important and why the bigger the sample size, the better, because it increases the power. And that's important because it gives you confidence that you're not committing a type 2 error. And no one in proper society would like you to commit a type 2 error. Okay, I was just joking again. The larger the sample size, the less likely to commit a type 2 error. Now we're going to change gears a little bit more. Clinical versus statistical significance. So in review, we've learned that a p-value of less than 0.05 is statistically significant. We've also learned that a confidence interval that contains 0 is not statistically significant. But we're not talking anything about clinical significance here. So that's the next thing. So this is clinically relevant. So it's like, great, yeah, p-hack your brains out, you doofus. So you get like an awesome p-value, but then is that clinically relevant for my patients? And that can be trickier to answer. And it's subjective depending on your opinion. You know, it depends on your patients, depends on what type of practitioner you want to be, etc. But it is one of the most important questions you have to answer when evaluating a study result. So always keep that in mind. Because again, like I said, the drug reps come in all suited and booted and giving you donuts and other things that that are sweet. I guess I don't know what I'm sorry. I didn't have lunch here pretty soon. I'm losing my mind. Lost my mama, lost my mind. Okay. But yeah, it's very important to think about the clinical significance and not just get hung up, because sometimes, and I did this too in journal clubs, you're a student, you're just like, yeah, the p-value and the power and type 1 error, type 2 error, the null, and you're all rattling all this awesome stuff off, which is great. And no disrespect to students or disrespect to my previous self when I was a student. But then it's like the preceptors always be like, is it clinically significant? That was always like their, talk about the clinical significance was always their thing that they like to get us with. So with the p-value of 0.01 and a good study design, you can prove, quote unquote, almost beyond a shadow of a doubt that something is statistically significant. But does it matter? So we're going to pick on this study to illustrate my point. So you link here to the study. Don't worry about going there and reading the study or whatever, but if you want to. So right off the bat, solid peer-reviewed publication. Study took 2,209 patients, good sample size, suffering from recurrent cold sores, and measured the lesion healing time of a group treated with this antiviral cream compared to placebo group. The study noted a reduced lesion healing time with the medication to 4.8 days, compared to placebo, which was 5.5 days. This sported an impressive p-value of less than 0.001. That's 2 zeros, homie. That's a tiny, tiny p-value. So you're like, what? That's statistically significant. And you're like giving all your homeboys high fives and stuff. Like, yeah. And you're all excited in journal club. And with a sample size that large and a p-value that small, there would be very few people that would argue against statistical significance. But 4.8 days, really that significant compared to 5.5 days. So clinical significance comes in here. So it's less than a day. Is that really better? Is it really worth taking the medication? Is it really worth the cost of the medication, the potential for side effects, having to go to the pharmacy, having to get a prescription, having to go to the doctor, etc., to get this prescription, even written, etc.? So definitely, yes, statistically significant, but then clinically, maybe not. And maybe it is too. Okay, so like, I don't want to judge all your future patients and stuff, but maybe that less than a day is clinically significant and worth a ton of money for somebody. So again, that's going to be a really important question that you're going to have to answer. You know, what type of practitioner you are, what type of patient population you have, and is this clinically significant for me, for my patients? The concept of clinical significance is also related to internal versus external validity, which we'll talk about a little bit more later. So you guys are all probably like this now at the end of my lecture. This is my imaginary lecture group. I have a poster size printout of this in front of me, and it's just inspiration. It's just, I feel like I'm back in UTRGV lecturing you guys on biostats. That was it. Oh yes, that was it. Okay, I'll talk to you guys later. Part 2's coming up. I probably won't record it for maybe in a day or so. I don't know if I want to do that today. All right, talk to you later. Bye.